So for our agenda for our webinar today, we're going to be talking about exactly what is model-based definition, why we want to use model-based definition, some of the helpful tools that come with the PTC products that we provide to get you started with model-based definition. And then we'll end with how do we take model-based definition and use that to create a model-based enterprise. So what is model-based definition? MBD defines the source of the product and manufacturing information as the 3D model. So the goal is to provide a single source of truth in the 3D model for downstream partners, such as manufacturing, quality, inspection, and suppliers. And it all starts with an annotated 3D model. So it's really not as complex as some people may think. It really all starts with taking your 3D model, taking your annotations, and using them in your 3D model to define your product. So using MBD, the 3D model replaces our 2D drawing as a source of our product and manufacturing information. So let's talk a little bit about the traditional methods, traditional processes around modeling and defining our product versus the digital processes that come with model-based definition. So for traditional processes, right, a lot of the customers that we work with use the 2D drawing as the legal asset that describes and defines our product. And really this is the case because before 3D CAD even was available, 2D was the standard format and the primary engineering deliverable that defines our products. And what we see with a lot of customers today, about 90% of them still use this 2D drawing as our legal asset, as our product defining documentation. And there's a couple downsides to this. And the first being that most of the time these 2D drawings are only human readable, right? So with model-based definition and this idea of digital transformation, taking all of our manual documents and transferring them to this digital process where not only humans can read this more efficiently, visually interrogating the models and the products that we're looking at, but it's also very, very, very easy for machines to read this as well. And like we said, MBD creates a single source of truth, right? With our 2D drawings and our models, we have two sources of truth. With our two sources of truth, if there's any differences between the two, we can start to run into problems such as nonconformances, such as our model not being correctly depicted by our 2D drawing. So taking that 2D drawing process and eliminating that, providing us with one single source of truth in the 3D model will help us with the efficiency of our design process. So what are we going to see with implementing model-based definition? We're going to see a decrease in lost time and effort just creating these 2D drawings. All of our information is going to be defined in the 3D model, so we have no need to actually create these 2D drawings, which will save us a lot of time. We also will see a minimize in rework and out of sync information, right? Having that 3D model as the single and only source of truth containing our product and manufacturing information. We'll also see we'll also eliminate the need to track and manage the additional assets and information. So all of our information is contained and managed within that 3D model. And what we'll also see is reduced errors due to misinterpretation and poor communication. So our 3D models are very easily visualized and interrogated for downstream users, such as people on the shop floor, right? The main thing with model-based definition is, if I ask the question, is it easier to envision what the product looks like from the 2D print, or is it easier to see what the product looks like from the 3D aspect? You know, most people are going to say it's much easier to envision what the product is going to look like from that 3D model. So right there, we have an advantage of having that increased visibility, increased knowledge of what our product will be like. And we have a lot of things that go along with it to help push that information to downstream users. All right, so talking about digital product definition and control. With model-based definition, we have a fully annotated 3D model. This 3D model is fully semantic, meaning that our annotations are directly related to our features, to our geometry in that 3D model. And because of this, we'll see faster product development. We'll see faster manufacturing and inspection processes. And finally, we'll see reduced errors and nonconformances because of that simplified complexity. And some of the feedback that we've gotten from some of our customers in regards to model-based definition and how they've implemented, how it's affected their company, we see 40% faster documentation creation. We see 60% reduction in the first article and inspection time. And finally, we see 90% less product nonconformances. So using PTC products that we provide, there's a lot of helpful tools that help kickstart you with your model-based definition. And one of these is GD&T Advisor. So GD&T Advisor is a tool that helps the user to create, validate, and educate the proper application of geometric tolerancing. So the tool provides a wizard-like dashboard to simplify and speed up the creation of semantically correct geometric tolerances. The user interface is easy to access. To these GD&T annotations, we have a feature tree that shows all of the features of our geometry, as well as an advisor tree that will show us error messages. It will show us warnings to make sure that our GD&T is correctly applied. We also have the ability to see exactly which services, which features are fully constrained within our model. And in the demonstration, I'll show you guys GD&T and kind of the power of it and how it can help you with model-based definition. The second tool we're going to be talking about today is Creo View. And with Creo View, we have the ability to interrogate models, interrogate documents without needing that native authoring application. So with Creo View, it takes these highly complex models, it compresses them down into a lightweight, viewable data object. So with this, we can bring up the data object, we can bring up the model, we can interrogate it, we can take measurements, we can investigate some of the properties of our product, and finally, we can create digital markups. So instead of having that 2D process, that very manual handoff, manually redlining our prints, we can now do this all digitally with Creo View. So without further ado, let's go ahead and look at Creo and model-based definition. All right, so I have Creo 8 open here, and today we're going to be looking at this model here, and it's a bracket that is first casted and then machined to create this final product here. And as you can see right away, we have annotations, we have notes associated with this model. And the way we do that is by creating combination states within our model. So you can see I have all of my combination states listed across the bottom here as tabs. So as we scroll through here, we can see different annotations that have been added to this model. And to manage these annotations, we can open up our view manager here. So in here, we can see we have all of our combination states that contain different information, different annotations that describe our product. If we wanted to, we could edit the definition for these combination states and specify certain options like orientation, simplified reps, cross sections, appearances, layers, and so on. So let's go through each one of these and kind of show what is being included in each one of these combination states. So on this first page here, we can see that we have some notes regarding our company, right? Some ITAR notice notes, some information about our company, as well as some proprietary information notices, right? And using the traditional process of the 2D print, a lot of this would be on the title block, right? It would be somewhere on the print. But with model-based definition, we can specify different combination states to separate some of these things. Next one we're going to look at is the sitemap. And this shows what our different combination states are going to show. So we have MBD2, which is the current state that I'm in, as the sitemap. We can see some information regarding the different features that are being created as this part is being manufactured. For 3, we have our titles. 4 is properties, 5 is notes, and 6 is datums. So let's check those out. In our titles, you can see we have our design signatures. So we have our parameters connected to our designers, to our engineers, our release records, as well as our checkers and check dates. And all of these are parameters that are managed within the parameters of this model. So we can go ahead and assign names to these parameters as needed. Next, we have our properties. And again, we're utilizing parameters in these notes here. So we see that this specific model has a material of aluminum alloy. And of course, we can add more information such as the material finish, material engineer. And then finally, we have calculations for the unit mass and the density. For number 5, we have any of the notes associated with this part. So in the past, right, we would have a 2D drawing. That 2D drawing would have notes that specify what we want to say about this product. But here we can just create a different state and show all of the notes that we want to describe about this. Number 6, we have our datums. So here, this is something that's really nice about model-based definition is we can, instead of trying to fit all of our datums, all of our annotations on one single view, we can really separate it out to give much more associative visibility to our product, right? If we have just all of our datums on one single state, we can very easily see that B obviously is this surface, right? Datum B is this surface. Datum A is this surface, right? And datum C is this slot here. And then as we get into the MBD7 combination states, these are all of the different processes that are happening to actually machine this part after it's casted, right? So we have our base holes here and all of the dimensions that represent the manufacturing of our base holes. We have our backside holes. We have our clevis slot and the dimensions that are associated with that. And then finally, our clevis holes and our bore here. Now, how do we go about creating combination states? And really, it's quite easy. So let's go into our annotate tab here. And in our annotate tab, we have some different things that we're allowed to do in creating these annotations. But the first thing we can do is we can go over to the left-hand side and see our combination states and create a new combination state. And you can see I have this new combination state that has been created in the bottom right-hand corner of our tabs here. So the first thing I'll do is I'll rename him. We're just going to call him MBD 7B. Okay. Now let's change the orientation of this. So let's go to one of our predetermined orientations. Now, once I select an orientation that I would want for this combination state, what I can do is I can say update. So I'll click on the update button in the top left here. Now, if I move this guy around, maybe go back to a different state and come back, that orientation is going to be saved for us. And we can change the orientation and keep updating it as we wish. But for now, we'll just keep this as is. So the next thing I'll do is I'll go ahead and start creating some annotations. So the first thing we're going to do is create a note. And before we do that, I want to talk about the placement of these notes. So we have these annotation planes, and as we hover over these, we can see what plane this annotation will be placed on, right? So let's go ahead and place it on the bottom plane, and then we'll place that note on this surface here. And we'll just type in sample note. All right, so we can see that this note here is obviously not in the right direction. So to change that, we'll just change the orientation and flip that guy so that we can see him properly. Now, if I go and click on this note, what I can do is I can pull up our semantic query. Our semantic query will tell us exactly what this note is represented by. And we can see this surface highlighting here, right? So this note is referencing this surface. Now let's say that I wanted to include this note and we want to add some references to him. What I can do is go over to our references on the top left here, and I can add more services if I wish here by just holding down Control and adding these services in this little inlet here. But with Creo 8 and beyond, we have some added functionality for looping in our surfaces here. So let's say we'll go ahead and add this guy, and we can use this seed and boundary surfaces to collect all of the surfaces that are in between this surface and our outer surface. So now as I pull up the semantic query for our note here, you can see that this sample note is referenced by all of these surfaces that are highlighted in this kind of purple color here. All right, now we're going to switch gears and add a dimension. So let's go over to our CBOR combination state. And what we're going to do is we're going to add a dimension for these 4 holes here. So I'll go ahead and click on dimension. And you can see that it's very similar to actually using our 2D print process, right? Similar to annotating an actual drawing. The only real difference is making sure that you have the correct plane selected as you're creating these, so that it's easy to view within the orientation of our model for our specific combination states. So I'll go ahead and click on the front here, and we're going to dimension, like I said, these 4 holes. All right, so I've created this dimension here. And now what I'm going to do is I'm going to add a reference for this dimension to the rest of the holes that have the same dimension. So I'll go ahead and open up my references, hold down Control, and select the rest of these holes here. Now, of course, as we open up our semantic query for this, we'll be able to see that all 4 of these holes are referenced by that dimension. Next, we're going to add a tolerance to this guy. So as I click on my dimension, very similar to our 2D processes, we have the ability to add a tolerance, and we'll just say it's a symmetric tolerance of 0.2 inches here. And then we're also going to add some text here, and we're going to say 4 times that diameter to represent all of the referenced holes here. And if this were me, I'd probably change this orientation of this annotation here. We can very easily do that by changing the orientation by right-clicking. I'm just going to rotate this text so that it's more centered and easier to view as we open up this combination state. And there we have our created annotation. So you can see just how easy it is. It's very similar to the 2D process. So getting used to model-based definition and making sure that you have your combination state set up is really the only difference between annotating in 2D versus 3D. Next, we're going to add a geometric tolerance to this guy. And we are going to do tolerance of 0.2, max material condition, and we're going to delete these B and C datums here. We're going to change this to a perpendicularity symbol. Okay, so we've created our annotation. We've created a note, and we can see that these are semantically connected to our holes that are being referenced here. Next thing I'm going to do is I'm going to open up our GD&T Advisor application to interrogate our dimensions, interrogate our model to make sure everything is set up semantically correct. Okay, so as I open up our GD&T Advisor extension here, you can see that on the left, we have a feature tree that has all of the features included in our model geometry, as well as an advisor tree. And this is what sets GD&T Advisor apart, is this advisor tree here. So we have three different types of warnings. We have an information warning, a regular warning, and an error warning. And we can see as we click on these guys, if we want to get more information on why some of these things are going wrong. For example, we have this specified geometric tolerance is not allowed. If we want to know why this is not allowed, we can open up the more help or more information about that. And we can see that this specified geometric characteristic symbol is not allowed by the standard. So by the ASME standard, this symbol is not allowed. So let's go ahead and fix that. Let's go ahead and change that to the correct symbol here. So what I'll do is I'll click on our pattern, and we'll go ahead and edit that guy. So in here, we can see our dashboard, our user interface of creating the correct geometric tolerance for that hole, for that pattern of holes. Now, as I open up the symbol here, what GD&T Advisor will do is it will only allow you to pick the correct symbol for this application, right? You can see that we can't even pick on perpendicularity because it doesn't make sense according to the ASME standard. And position is highlighted in green, right? If we had other symbols that would work in this scenario, you would be able to pick on them. But what GD&T Advisor will do is it will highlight the most recommended symbol in green here. So we'll go ahead and pick on position. Now, as we do that, we'll just add our maximum material condition here, and we can see that it's automatically brought in our three different datums and recommending that we do that. We notice that the check mark has now changed from orange to green, indicating that this is now complete, and we can go ahead and accept that. Now, if you notice in our advisor tree, that error warning is now gone, right? So we now have the confidence that our GD&T for these holes is correctly set up. Another cool thing about GD&T Advisor is that we have the ability to see exactly visually what surfaces, what features of our product are constrained. So we can see that on the bottom left hand here, we have this constrained state legend. We can see that the fully constrained will be represented by a green color. So we can see all of our surfaces here that are fully constrained are highlighted in green. And then the rest of the surfaces that are not are unconstrained. Okay, now let's start addressing some of these other warnings here. And we'll start with this user-specific annotation property that is ignored. Actually, we're going to start with some of the surfaces of this design model are not constrained. So let's go ahead and go over to our datum state here. And I'll turn this guy off. And what I can do from here is I can click on edit properties for this. Now, as I bring this up, our properties, we can see the tolerancing standard that we're using right here. If we had other tolerancing standards that we wanted to use, we'd be able to select them from here. But what I want to do is I want to constrain all of those surfaces that are not constrained. And what we can do is we can actually use a note to constrain those. We can use our general profile note to constrain those surfaces. So I'll go ahead and bring him over, and we'll give him a tolerance of 0.3 and hit accept here. So you'll notice that it brings in that note. And what it's going to do is it's going to bring in that note to all of our combination states. because it is represented in all of our states. Now, as we open up our constraints here, we can see that we have our green fully constrained features still there, but now we have a constrained by surface profile in our note here. So now we have a fully constrained part, and we can go ahead and address our other warnings here. So next, we are going to look at this warning here. So we have a warning that says user specified annotation properties ignored. So what we're going to do is head over to our clevis holes here. And we're going to pick on, I'm sorry, we're going to go back to our datums here. I apologize here. I'm just double checking here. Okay, let's go back to our clevis holes here. Okay, and we can see that we have this annotation here that says 4 places, right? As we click on our user specified annotation properties ignored warning, we can see that our 4 places and our GD&T connected to this dimension, it highlights, right? So there's something wrong, something that needs to be fixed with this. So what I can do is I can click on this, and we'll go to our annotate tab. And remove that 4 places text there. All right, so as we updated that, as we got rid of that additional text, we now see that that warning has gone away. Next thing we want to do is address these other 2 warnings here. So the next one we're going to look at is the model contains annotation mismatches. So to address this, we're going to go back to our correct view here. And actually, what we can do from this, so we have these 2 warnings here. They say we have annotation mismatches as well as some unvalidated annotations. So we can address both of these issues by going into the manage annotations. And the first one we're going to look at is the mismatches. So we can go ahead and click on this. And all we have to do is say update selected. Now what it did was it took all of the notes, all of the dimensions that were representing the same thing that were mismatched, and updated them to the correct annotation there. Now the final one we're going to do is we're going to look at the manage annotations and solve this last warning here for our unvalidated annotations. So let's go back to our CBOR combination state. And we're going to go into our manage annotations again. So we can see that this is unvalidated, right? This 4 places is causing this GD&T advisor to have this error warning, right? Because really what should be happening is we should have that 4 times that dimension. So what we can do is we can select this guy. And what we can do is delete that text that is causing that issue, and replace it with our 4 times. Okay. So that was GD&T Advisor. It really does help with solving some of the issues that you're having with your geometric tolerances, making sure that your part is fully semantically and correctly annotated with your geometric tolerances as well as your regular tolerances. Okay. Now we have our model here. And one of the questions you may be having with model-based definition is, right, how do we print this? How do we share this with the rest of our company? And there's a few different ways to do that, right? The first way, if we want to print out some actual representations of these combination states, is we can literally just print this. So if we go over to print, we can pick a range so we can define which combination states we want to see. So let's say that we wanted to see maybe just the modeling, the manufacturing processes that actually make this product. I'll click OK to that, and we'll go ahead and click OK here. It'll go through after we select. We're just going to print this to a PDF here, and I'll just save it to my desktop. We'll save it as MBD. So now I'll go through and physically print these to that PDF so that we have those in that PDF, in that 2D shareable documentation. So as I go back over to my desktop here, we can see, where's my MBD? Oh, here it is. We can see it printed out, all of those combination states, basically showing, the 2D version of our model-based defined model. Now, an even better way to do this, an even better way to share this out to the rest of our company is to utilize Creo View. So what we can do is we can save this as a PVZ file. So I would click on PVZ here for Creo View, and I'd go ahead and save this to open up and interrogate in Creo View. So as I open up Creo View here, we can see that we have all of our different states. We can click on them, we can interrogate them, and see all of our annotations that have been created for this model-based definition example here. Now there's some other tools that come with Creo View that are really awesome. Honestly, what we can do is we can digitally take measurements. We can digitally mark up our model and our different states, our different representations of our annotations, and so on and so forth. So let's say, for example, I wanted to see the mass properties of this part. What I can do is measure mass properties, and it shows me the name, volume, mass, center of gravity, and things like that. I could also take length measurements, distance measurements, angles, diameters. And the nice thing about this is that it's a very lightweight, model in here, right? So it took our very complex, data heavy 3D model, it compressed it down into a very small, lightweight, viewable model where we can still interrogate it. We can still take measurements, create markups, and so on and so forth. Now, let's say we go over to our CBOR state here. And let's say that we wanted to maybe get rid of this datum. We don't want this datum showing up here. So if I was a manager and my engineer sent me this Creo View file of our model-based model, what I would do is I'd probably just create a markup here, maybe highlighting this datum, and then I'd add a note saying, remove datum from the combination state. And we can go ahead and add a leader on here as well, just to show some better visibility as to what we're talking about. I could also add another note here and say, maybe we want to double check this tolerance of this annotation here. And I'll create a leader and show that I'm talking about this tolerance right here. Now, once I have marked this up, what I can do is I can save this annotation set. And I'll just name it markup 1. Now, in this PVZ file, in this Creo View file, that annotation has now been saved to this file. So instead of actually taking the physical print, the 2D print that's hard to visualize, hard to interrogate, we can take this Creo View file, we can spin the model around very easily and efficiently, analyzing the actual geometry as it stands. And we can also create these digital markups as well. Now this markup, as you can see, is saved to this viewable. So as a manager, for example, we mark this up, we send it back to our engineer for them to mark up according to this annotation or this markup that I created for this part. All right, so I hope you saw that how easy it was to actually create model-based definition to fully annotate our 3D models. And with that, there's a lot of powerful things that we can do with those 3D models. We can take those models and we can do things like create bill of materials, highly visual, highly associative bill of materials. We can create specifications from this. We can simulate FEA analysis, take those analysis from this model. And from this model, we have all of our product and manufacturing information contained in this single source of truth in the 3D model. Now, the model-based enterprise is an organization that uses model-based definitions for the purpose of commission, operation, service, and decommission of a product. So while MBD refers to the data, MBE refers to the enterprise that wants to reuse that single rich source of truth in the 3D model. And typically the enterprise will want to reuse the data throughout the whole product lifecycle. So for example, you would want to take that information and reuse it as part of your manufacturing process planning, as part of your quality inspection, as part of your assembly work instructions, and so on and so forth. Now, being a customer of ours or PTC, using PTC products is a major advantage in the model-based enterprise, because PTC products such as Windchill, the product lifecycle management tool, enables a model-based enterprise. So if you've heard discussions from us or any webinars, we've talked a lot about the digital thread. And the digital thread is the seamless flow of data up and down the value chain, connecting each phase of each sector of our company to that product lifecycle, from design to testing, production, and to service. Now, what we can do with this model-based definition, with this 3D model that contains all of the information needed to define that product, is we can take that 3D model and we can use it for different downstream activities, such as creating highly associative bill of materials, right? We can create engineering bill of materials, we can create service bill of materials, manufacturing bill of materials. We can take this data and we can use it for simulation. We can use it for quality engineering, right? We can take all of that information and externalize that, provide it to our necessary quality people for them to take measurements and making sure that the quality of our product is up to standard. We can also use this fully associative 3D model that's fully annotated for work instructions. We can use it for the shop floor. And like we said before, right, is it going to be easier for our shop floor person to read a 2D print, or actually be able to see the model, see the annotations, spin it around, and get a better idea of what that end product should actually look like? So using Windchill in combination with model-based definition will enable a model-based enterprise. Now, I want to show this maturity matrix for model-based definition, and I want you guys to kind of listen in and try to figure out where you are on this maturity matrix and where you might want to be in this maturity matrix. And we'll start out with kind of the baseline, which is a drawing-centric approach to our product development, right? This is where we have our 2D master drawing, and we don't have a 3D model. If we do, it's not verified, it's not configuration controlled. And, you know, there are plenty of companies that are here. There are plenty of companies that only use 2D. They don't even have the capability to produce 3D drawings, right? And then the next step would be a model-centric approach. So this is where we have our 2D master drawing as that legal asset, as the describer of our product with an associative 3D model, right? But this model is still not verified, still not configuration controlled. The next step would be our model-based definition, where we get rid of that 2D drawing. We just have our 3D master and CAD model with our 3D annotations. And we can derive that 2D drawing if needed, but it's going to be coming directly from our 3D model, our single source of truth. And then finally, we have our model-based enterprise. So this is where we have our model-based definition. We use that to connect our digital thread, to connect the different sectors of our enterprise, to have a very cohesive flowing of information regarding our product development. So I want you to take a moment and think of where you are and where you might want to be in this maturity matrix for model-based definition. So as you can imagine, model-based definition is kind of a hot topic lately. Many companies are starting the transition over to model-based definition. And with that, although it's not widely used across the industries, studies have shown that 84% of products from the best in-class manufacturers using model-based definition achieve revenue, cost, launch, and quality targets. So it's really, there's really been a push to incorporate model-based definition. It's really proving to be efficient for the people who are actually using it. And then finally, I'm just going to end with some of the customers that have fully committed to using model-based definition, using PTC products, right, using Creo. And you can see some of the names on here, some big manufacturer names: Boeing in the aerospace industry, Raytheon and General Dynamics in the defense and heavy equipment. Toyota is using fully model-based defined models, Rolls-Royce, and you can see a whole list of all of the others, all of the other customers that have been fully committed to MBD. So this is not something that is not going to help your company, right? These big companies are transitioning to model-based definition because it is making their product development much more efficient, and it's helping them to create a fully cohesive, fully visual and associative digital thread as their products are going through that full product lifecycle.